mechanism, if you will, of retention in gas chromatography, in gas-liquid chromatography, and that's what we call interfacial adsorption. It's not necessarily bad. Usually we try to avoid it. When it happens, it can cause some pretty ugly looking peaks for some compounds. But it also generally just makes life more complicated. Sometimes it improves the selectivity of the separation, and in that instance it can be good. So you may not always want to have no interfacial adsorption, but if it causes a bad peak shape, then you've got to get rid of it. But we'll talk about that, and then we're going to get deep into choosing stationary phases for gas chromatography. There's something on the order of 500 different kinds of GC stationary phases that you can buy from somebody. And picking the right one is a challenging proposition. It certainly depends very much on the sample and the type of sample that you're dealing with, and whether you're doing trace analysis, meaning very low concentrations, or just higher level analysis, which you have a lot more latitude in what you can do. We're going to look at one of the key issues in retention, and that's the number of CH2 groups. The number of CH2 groups in the molecule, and that leads to what we call the Martin equation in chromatography. I guess it's one of the Martin equations. That says that the logarithm of the retention factor is a linear function of the number of carbon CH2 groups in a homolog series. And that is something you can bet on, except for perhaps the first one or two members of a homolog series, like methanol, ethanol, or acetonitrile, propionitrile. As you add CH2 groups, you're going to see a linear increase in the logarithm of the retention factor, and things linearly related to the retention factor. And this in turn is very useful in reporting retention, and the Kovatz index is a very useful measure of retention over and above retention volume or retention factor or adjusted retention factor. In fact, you can go and get tables of Kovatz indices of tens of thousands of compounds on many different stationary phases. And this in turn will lead us to a set of rules of thumb that allow you to estimate retention in gas chromatography. So let's get to this interfacial adsorption business. This diagram represents the 5 regions in a conventional packed bed GC stationary phase coated on a porous support. So this is supposed to represent some region of space inside the GC particle. It's not the outer surface of the particle, it's interior of a pore. And what we have on the inside of the pore is we have gas phase. That's region number 1. That's the mobile phase. Then region number 2 is the thin film. The thin film of the stationary phase, where partitioning takes place. Region 3 is the solid support. Region 4, over here, is the interface between the liquid phase and the support particle, or the liquid-solid interface. And it's possible that the analyte will adsorb at that interface. In other words, it likes the solid, so it's going to try and sit on the surface of the solid rather than be dissolved in that thin film of stationary phase liquid. And the fifth region is here, and that is the interface between the gas phase and liquid phase. And sometimes molecules will want to adsorb at the gas-liquid interface. Now, the equation for beta that I gave assumes 100% partitioning. In other words, it says there's no interfacial adsorption, either gas-solid or gas-liquid. But these things do take place, and as I said, certainly in the case of the gas-solid interfacial adsorption, you can almost bet that that's going to give you pretty bad peak tailing. So we really try to get rid of that as much as possible. And that, of course, takes place at that interface. Okay. So what I'm saying is that your adjusted retention volume, the VR prime, which is the retention volume minus the dead volume, that's equal to the beta WS, which is the partition contribution, and we certainly want that to be the dominant contribution, plus the interfacial adsorption contributions, and that depends on the equilibrium for interfacial adsorption, either at the gas-liquid interface or at the gas-solid interface. Now, the interfacial adsorption effects don't really care about how much stationary phase liquid there is. They care about the area available for that kind of adsorption process. So the gas-liquid is governed by the external area of the liquid phase, the liquid-gas interface area. And the gas-solid depends upon the area of the solid interface. One of the really good advantages of capillary GC that's often people don't think about is these two areas in capillary chromatography are much smaller than they are in packed bed chromatography. So that definitely benefits you, and it minimizes your interfacial adsorption effects. So these equilibrium constants are the equilibrium constants for the adsorption process. So I'm just going to show it for the liquid interface here. So we have the concentration of the solute in the gas phase in equilibrium with the concentration of the solute at the gas-liquid interface, and we represent that ratio as this distribution coefficient. Now, if we take this top equation and divide out WS on both sides, so we're going to look at VR prime over WS. That divides that out, so all we get is beta here. And then we get the interfacial adsorption contributions divided by WS. Now, if there's no interfacial adsorption, and you make a plot of the adjusted retention volume divided by the weight of stationary phase versus 1 over the weight of stationary phase, and there's no interfacial adsorption, all you have on the right-hand side is beta. So if you make a plot, the slope of the plot's going to be 0, because you've said the numerator here is 0. All you've got is the partitioning process. But if you have interfacial adsorption, then a plot of VR divided by WS versus 1 over WS is going to have a slope to it, and it's got to be a positive number. So if we have VR Interfacial adsorption is going to look like that. Now, when 1 over Ws is 0, in other words, you've got an infinite amount of stationary phase, which is kind of hard to get. But if you extrapolate your data, that's going to give you your intercept beta, your partition coefficient. And the slope of that plot is going to give you the sum. The slope of that plot is going to give you the numerator. Okay, so the problem with interfacial adsorption, of course, means that if you try to prepare 2 columns and you use different amounts of stationary phase, if you have interfacial adsorption, your adjusted retention volume is going to be different. The adjusted retention volume relative to the weight of stationary phase is going to differ on those 2 columns if you have interfacial adsorption, which could be quite confusing. But if it's pure partitioning, you get the same number. But there are other issues. One of the bigger bugaboos is surface wetting. In order for the stationary phase to form a reasonably uniform film, it has to wet the surface. If, for instance, if you take a drop of water and put it on a room temperature Teflon coated frying pan, you see a bead of water. That's anti-wetting. Teflon has the unique property that is not miscible either with polar things like water or with non-polar things like fat. So if you take a drop of olive oil and put it on a Teflon frying pan, it also beads up. Olive oil is a rather non-polar substance. Organic compounds do tend to wet organic compounds, and water does tend to wet polar surfaces. So the underlying surface of silica, fused silica, the underlying surface of packing materials like diatomaceous earth, are polar. So how do we get organic compounds to wet a polar surface? We make the polar surface non-polar. We use silanization chemistry. But it doesn't always work. And you get some very strange results when you don't have wetting of the stationary phase. I don't want to go into any more detail than that. But the basic problem is if it doesn't wet, you're going to get very strange looking plots of your specific retention volume, which is VR prime over WS versus WS. It's not going to be linear, it's not going to be flat. It can actually show maxima in it. It's weird, and usually the stationary phase, the peak shape is terrible, the HETP is terrible. This is not something you want. You want to get a thin film. Okay, so that said, there are only 500 liquids or so used to make GC phases. Liquids have to have rather specific properties to be useful as stationary phases in gas chromatography. So let's think about that. What do you think the important properties are of something to make it useful for doing GC as a stationary phase?
Really viscous.
What?
It has to be really viscous.
That's certainly one of them. That's right. It has to be viscous like that because it'll stay in place. It won't run off of the particles and form a big puddle. That's definitely one.
Can't be reactive with the compounds?
Well, with the compound or with the support, because it's going to be hot. Most of its life it's going to be hot. That's right. So it can't be reactive. Another way to say that is it has to be thermally stable. What else do you want?
High boiling point.
Why?
Because
That's right, but why?
In the oven, the temperature will be really high, so we don't want the stationary to evaporate.
You don't want it to evaporate and come out of the column. So we can't use hexane as a stationary phase. That would be really, I've never seen it used as a stationary phase. It's even hard to use octadecane as a stationary phase. There's actually quite a few things that you have to have in play to make a liquid a good stationary phase. It has to be non-volatile. That's the first thing. You can't use low molecular weight liquids or non-polar liquids. It's got to be thermally stable. It can't react in the column. It can't react with things that you shoot in the column. Usually has to be low melting. It's kind of hard to coat a solid with a solid evenly. Now, in order to coat something like that with that kind of viscosity on particles, you have to dissolve it. You've got to put it in a low viscosity solvent so you can coat it. And then you just heat off the low viscosity solvent. You want it to adhere to the surface, meaning you want it to wet the surface. But there are still additional issues that are important. The stationary phase liquid has to be a good solvent for the stuff that you're trying to separate. If it's not, you're not going to have a good linear isotherm. You're going to saturate the stationary phase liquid with your sample, and look, it's going to bend over, and you're either going to get tailing or you're going to get fronting, depending upon circumstances. So you want it to be a pretty good solvent for your analyte. Really, one of the most important characteristics is you want different compounds to have different affinities for the stationary phase, because that's where the selectivity of the separation kicks in. So you want it to be a good solvent for a lot of things, but you want it to act as a differential solvent as well, so that compounds have a range in solubilities in it. And typically, these are high molecular weight silicone polymers. Here's a page out of a catalog. I don't really remember whose catalog it is. But let's look at SPD-1. The polymer is a polymer of dimethyl siloxane. So the repeat unit is OSI CH3CH3. OSI CH3CH3. No one says polydimethyl siloxane. That's PDMS. You say it as fast as you can. PDMS. Most of the others shown here are siloxanes, where you leave one methyl group and substitute the other methyl group with, say, a phenyl group, or a propyl group, or a propyl cyano group, or you have like this one here is a diphenyl, dimethyl, and then you would vary the proportions of the diphenyl. This is 5% diphenyl, 95% dimethyl, on up to completely diphenyl. Here's a phenyl, and then a dicyano-propyl. So it's a cyano-propyl phenyl, dicyano. how many of these things you can make, right? I mean, it's almost an infinite possibility. But there are other high molecular weight compounds and polymers that are used, for instance, polyethylene glycol. This is carbowax. This is a very famous stationary phase. There is an OH group on one end of this polymer, which makes it a strong hydrogen bonding agent, but in the middle, it's just ethylene oxide. Repeat, 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 no siloxane. Here's the catalog had a lot of pages that look like this. These are all different GC stationary phases. It goes on and on and on. This is an important note. You'll see right here that they offer to provide a bunch of numbers called the McReynolds values, which I'll get to in just a few seconds. But any company will always be willing to provide you with this set of numbers, the McReynolds values or the Rohrschneider McReynolds values for all of their stationary phases, because it's helpful in choosing which stationary phase to use for your application. I have a very simple rule of thumb for picking a GC phase. Find an application note on compounds that are similar to your compounds, preferably identical. And if it worked, that's the stationary phase you want to use. And these companies put a big pot of money into developing application notes for all of their stationary phases. If the company doesn't have applications notes, don't do it. It means you're going to have to do it. Here are some other stationary phase materials. Any high molecular weight phthalate you can imagine has been used. This is di-isodecyl, dinonyl, dibutyl phthalates have all been used. Sebacic acid is the CH straight chain dicarboxylic acid, and make the C8 ethers on esters on either end. Tricresyl phosphate, this is a really polar stationary phase. Hundreds and hundreds of liquids are used, and the data is out there for them. I have to tell you about this stationary phase, even though the chances of you ever using it are close to zero. It's called squalane. I certainly don't remember where the methyl groups are. That's where the methyl groups are. It's a perfectly symmetrical molecule. The name is squalane because it comes from shark oil, squalene, L-E-N-E, meaning the unsaturated compound. You just hydrogenate squalene and you get squalane. It is, by very general use, the standard of low polarity. This has so many carbons that it's non-volatile. It's got no polar functional groups. It's also interesting material, even though it's such a high carbon number, its melting point is below room temperature. The way you lower melting points is to introduce a lot of branch points in a molecule. And this has got 6 branch points, so it's a liquid at room temperature. But it's used as the basis of non-polarity, and we'll see where that's important in just a few seconds. If we plot the specific retention volume, which is just the adjusted retention volume divided by the weight of stationary phase versus carbon number for 2 homolog series, this is the N-alcohols. Okay, so this is Well, that's decanol, nonanol, octanol. No. Sorry. The blue is the alcohols, the black, the lower vapor, the higher vapor pressure is the alkanes. You can see that the blue becomes more retentive at lower carbon numbers than the black because of the OH group. It's going to interact with lots of molecules. I forget what the solute is here. This is carbowax. Oh, these are the solutes, and it's the stationary phase of carbowax 20M. The 20M indicates its molecular weight, but there's only one OH group at the end of the chain. The rest of it is just ethers that are repeated and repeated and repeated. You can see that the alcohols are more retained than are the N-alkanes of the same carbon number. If we take the logarithm of this specific retention volume, oh goodness gracious, I just started talking. Sorry, forgive me. It just seemed like I just got started. Just let me finish this one point. The log of the specific retention volume, or the log of the retention factor, or the log of the adjusted retention volume or retention time, linear function of carbon. These are measurements. You can see this is not so linear, but then it becomes nicely linear. The alkanes are really very nicely linear. This is very important to us, as you'll see when we get a little further. Okay.